Greetings. This is Graham Warren working with you on the juice bar model. So this is AnyLogic. I've put together a model here to do this. I think it's a little bit more sophisticated than what maybe a first timer would be able to put together. But I think seeing something like this is also interesting. So the juice bar setup is one that is it's a case study where there are two people who own a juice bar at an airport. And currently, customers arrive at this juice bar and line up in separate lines. And the customers join these separate lines at the rate of 65 per hour in a Poisson process. They get service from a human server. The humans are currently not very well trained, providing service with roughly a normal distribution. Of course, non-negative service times, and a strict normal distribution would give you potentially, with low probability, negative service times, but approximately normal, with a mean of 40 seconds and a standard deviation of 20 seconds. So we're going to be able to estimate the initial performance of that setup. And then there's a bunch of options that involve pooling the lines, pooling the servers to serve a single line instead of having them form separate lines. In other words, the separate line behind each, we're trying to get service from each server. Getting some training for the servers, doing both the pooling and the training. And then there's this option of a juice bot. The juice bot is an automated server that would serve in a deterministic, in other words, constant service time of 50 seconds, no variation. And there's potential for or an opportunity for that juice bot to replace one of the servers. Okay, so that's our setup. I want to go through the model in this initial clip, just to explain what's going on, and then we will do the analysis of each of these scenarios, in separate or maybe a couple to a clip. So there's a sync block here. So firstly, I went ahead and created this model, and it's called the juice bar model. So if you click on this, you can see that I named it juice bar model. So when you first do and create a new model, you're going to get this opportunity to name your model. And I also chose seconds. And the reason for that is, it's purely convenience. You can change it to minutes right now if you so choose. But it just turns out that the waiting times in this particular case study are perhaps best expressed in seconds to get the resolution that we need to sort of evaluate what the best option is. Right. So this is AnyLogic, and I have the project panel open. When you're developing a model, your central canvas here will be empty. And you're going to be dragging and dropping these various blocks, so-called blocks, onto the canvas to put together your model. Now, the process modeling library is the one we're going to be using here. And there's a bunch of, sort of very standardized blocks that are typical for this software and many other similar softwares that can be used to build these so-called discrete event system models, DES or DEMs. Right, so I'm going to need a block in this DEM to create customers, and that's this source block. So I'm going to click on that and just show you what I did. I'm going to just use the rate mechanism. The customers are arriving. So currently I'm just going to analyze one of the servers with Poisson arrivals and normally distributed service. So this is in fact an MG1 model that we're building here. But it's a little fancy because I want to build one model that can serve the analytical purposes of our entire case study. So I have these Poisson arrivals. It just turns out that if you use this rate mechanism, I could have gone ahead and specified an inter-arrival time distribution. It made that exponential. That would then correspond with having a Poisson process. But turns out that I can just go cheap here and just put in 65, and that is going to give you a Poisson process. That's the sort of default assumption of AnyLogic, that if you specify the rate, that these arrivals are occurring according to a Poisson process. And then I've gone ahead and put in a couple of timers, and the timers come from down here: time measure start, time measure end. And every time you put one of these blocks in, you get an opportunity to relabel it. And that's what I've done to kind of just make it a little bit easier to read. So this is just a timer, 2 timers. The first timer is going to measure the time in the system of a customer. In other words, the time of arrival to time of collecting the beverage, the end of the experience. And then timer 2 is just going to measure how long do they wait in line prior to getting service from the server. Okay, now I've got a couple of interesting features here. These are resource pools, and I want to do a generic model that's going to be able to accommodate all of our needs, analytical needs. And so there are scenarios where we have human servers and the JuiceBot, and so I'm going to create resource pools. So the human servers, this is actually a resource pool, and you just create one of those using this block here. Just drag it in, and then I've specified it. It has a capacity. So currently there's 1 human server. And I think I only did one other thing here, that is to check this force statistics collection box. Same thing for the JuiceBots. There are currently none in there, no capacity, because the initial setup is going to be just to analyze one of the servers in isolation. Coruscant arrivals coming at rate 65. They're providing roughly normal service with a mean of 40 seconds, that deviation of 20. Question is, what's the waiting time in the line? Question, and then also their waiting time in the system. All right, now this C's block grabs one of the resources. I'll show you what that looks like now. This is a little complicated, but there are 2 types of resources: human servers and JuiceBots. And so it can grab either one of those. When they're in separate lists like this, it's one or the other, alternative resource sets, just grab one. So there are no JuiceBots to grab, so it would never be able to do that. But if there is a human server available, that human server gets grabbed, the customer gets served, and then at the end of the service, we're going to release the resource. So that's the idea of these resource pools. All right, then I'm going to just, snap my stopwatch to collect the time for how long that customer was in line, and then they actually go and get their juice prepped. Now this is a delay block, and it's a little interesting because I want to just show you this delay time. This is a bit of Java here, so it's not a beginner's model, but the basic idea here is I'm checking to see if the customer has an attached human server. So there are 2 types of server, 2 types of resources, right? Human servers and JuiceBots. And if there is a human server attached to the customer coming through, then the service time is going to be normally distributed with a standard deviation of 20 and a mean of 40. AnyLogic's got this weird convention of putting the standard deviation before the mean. And if that's not true, in other words, it's a JuiceBot, then it's going to be a flat 50 seconds of service time. So I think the logic here is relatively straightforward. It's just that getting that together, to be frank, it took me quite a while to get the syntax working, and the debugging was rather painful, but now it is. And so now you can see it, at work. All right, so now we've got the person delayed for the juice. So the juice is prepped. When they're done, we snap the stopwatch again to figure out, how long their wait in the system was overall. That is the time in the line plus getting service, the beverage prep, and then we release the server, whether it's a JuiceBot or a human, and then that customer goes to sync. We're going to dispose of the customer. So customers are randomly generated and then run through this process and then get disposed of. I'm also collecting statistics along the way here, so I just want to show you that I did check some of these boxes for statistics collection, and I think I didn't have to adjust anything on that one. Now I've got some information that I'm collecting here. I'm going to use something from the analytics panel here, and it is a histogram. And I have gone ahead and connected this histogram to the timer, timer 2. You can see how I've done that. Timer 2 end. I'm going to go and get the distribution of those times. I'm also requesting a mean. Okay. And then for the first timer, which measures the time insistence, so timer 1 measures from timer 1 start to timer 1 end. Timer 2 start measures, timer 2 measures the time from timer 2 start to timer 2 end. You can have a look at these timers, and you can see how I've connected the start. Yeah, so timer 1 end is connected to timer 1 start, and timer 2 end is connected to, guess what? Timer 2 start. And then these histograms are going to go ahead and collect the distribution of those waiting times in line, waiting times in the system. Okay, so I think that is our model. I'm going to end this clip, and then in the next one, we will do the actual experimentation. I do need to walk you through some of the details of the replication and just looking at the output.